Everybody, my name's David. I'm from Meta. I'm here with my colleague Ryan. Today we're going to be talking about how to make LAVD work on our servers. This is kind of a continuation of our talk in LPC. So today we're going to try to look at how well the Wakey heuristics work on large server workloads, and what are some of the pitfalls in design and some of the roadblocks we've run into, and also talk about some new kind of task placement strategies. So we know LAVD does these metrics are based on Wakey heuristics to determine how important a task is, or if it's in the middle of some critical chain. So we can use that information to try to make, place tasks on different CPUs. So the current status is we did roll out LAVD at scale on multiple major services, and as a result, there was some amount of revenue gained from some of the latency benefits that we've seen. So here this is one of the case studies we're looking at. This is some large front, user-facing service. And if we follow sort of this request that's coming in from the client, as part of that request chain, it has to talk to some caching service in the back end, or it has to talk to some databases. And as a result, there's this chain of wake-ups that happen throughout the lifetime of this request. And how LAVD views this particular chain is that there are these small threads that wake up very often. So LAVD would see these as "quote unquote" more critical to the system. And as you can see, the wake up frequency is tied to how LAVD views as latency criticality. And what does this translate to for the service? So in general, or at least for this particular service, we measure that the tail latency tends to be much lower for LAVD, in the normal case, or rather in non-contented cases, the wake up latency isn't so bad. But as we increase contention or during periods of bursts, we see LAVD having much shorter wake up latencies. And this is a lot of this is due to the fact that we have shared DSQs per LLC, which just means that if a task gets queued up, it's likely to run. It's likely to have a available CPU. And the trade-off here is now we have a lot more migrations, and that does hurt your L1, L2 cache locality. So we do measure a small throughput hit. And this is sort of the trade-offs that we have to make. Is tail latency much more important for this service? And in this case, it is. This is kind of what we're observing. And the other aspect is LAVD's wakey kind of heuristics. So you're more likely to have smaller tasks, or at least more critical tasks, run in front of the queue, and they tend to have, again, lower scheduling latencies. So we're going to move on to a different use case. This is a backend caching service, and this is where an example of maybe the heuristics not working as well as intended. So typically, a packet comes in, some KSoft RD work will then wake up this cache worker. It handles that caching request. If it's in DRAM, it's a hit. And the critical path that we're interested in is the cache miss case, where we have to do some reads on a disk, and then we have to wait for that response to give us a value for that request. So I think the thing we want to highlight here is, even though the reader is part of that critical path, we actually have more wake-ups for the writer. And this is because the service has purposely tried to delay the workers for the reads, such that you have more batching, and the writers actually fire forget, where we may not care about having the immediate response, but it's sort of eventually important. But LAVD actually kind of has that inversion in this case. So even though it figures out, hey, these cache workers and cache libs are actually really important, but in this case, it actually thinks the writers are actually more important because of that particular heuristic. And with KSoft RQD, because you're looking at the waker in this case, if you're waking from swapper or idle task, then it doesn't actually see it being woken up by anything. So LAVD actually sees that as, lower in the latency criticality aspect. So, we can add a little heuristic to boost that particular thread a little bit more. And this is where we think maybe user hinting could help to boost, if it's purposely delaying the reads, maybe it can give it a little more boost in the criticality aspect and bump it up in terms of criticality. The other interesting aspect about this use case, as we presented back in LPC, was there are a lot of interrupts that are happening, and they're very sporadic. So, as the system load changes, it can go from having tons of interrupts and having slowed down. But as we can see, for these cache workers, which we know are important, are getting tons of their time being stolen by the soft hierarchies, up to a quarter of their time on the CPU. And what this translates to, or one of the reasons why this happens is LAVD has these task stealing heuristics. So what you see is the cores with the IRQs on them really struggling, because when the CPU wakes up, it tries to steal from this shared queue and has no aspect of knowing that there's IRQs being hit on the CPU. So the cores are actually, at 98%, 99% saturated, while the other cores are more idle. And there's sort of this imbalance. Whereas EVDF is aware of IRQ load and IRQ pressure, so it's able to do a better job of load balancing between the different CPUs. So can we do a little bit better? We know LAVD already tracks which tasks enter these critical sections, which are critical. And we know that CPUs aren't equal. Some CPUs are more susceptible to latency or steal, or from other scheduling classes. We can classify these as more turbulent CPUs. And then we know not all the tasks are equal. So maybe what we should try to do is move what we think are important tasks away from the CPUs that are potentially more susceptible to being interrupted. And if we take a snapshot of the workload that we just looked at, where we have what we consider important tasks and not so important tasks, and we split them up into these buckets, we'll see that most of these really important tasks live right around here. And we can define this sort of new vulnerability metric as a way to say, we want to categorize these tasks into what we think are important versus not important. And then we use utilization as sort of a tiebreaker between when we want to maybe peel off certain tasks to keep the load balancing similar between two sets of groups of CPUs. Then that's sort of the general formula at the bottom there. So how that would work is, we would, if one side, so how we're tracking this is we're looking just at idle time of the CPUs, how busy are the CPUs. And we try to keep both of the groups of CPUs sort of in a similar idleness. And the idea is that, if we just look at latency criticality, then if we increase this step function, then we could migrate a bunch of tasks over to maybe the turbulent CPU. So the utilization is acting as a tiebreaker in the sense that, okay, maybe it's okay to steal some of these short-running tasks that are critical and still have the system behave okay. So if we look at how the queuing structure works, we have another DSQ as part of that CCX domain now. So we have the CPUs that can consume from what we call these steady CPUs, and then you have these RQ CPUs that are stealing from the turbulent DSQs. And the vulnerable tasks, depending on whether, what we consider to be some arbitrary threshold right now, if they are more vulnerable, then we try to find an idle CPU in the CPUs that aren't interrupted by RQs, and then we try to find an idle CPU in sort of the RQ polluted CPUs. And this is the result after adding this. So on the very left, you'll see that compared to before, LAVD was really struggling on the CPUs that have a lot of RQ work on them. But now you can see kind of the work being more distributed between each of the CPUs. And then if we actually just sample, this is a Perfetto trace, if we sample how much time is being stolen from those particular workers, this is sort of the before and after improvements after the fact. And what does this actually translate to in production? So when we look at sort of the tail, get, and sort of delete latencies for these caching servers, at least in periods of burst is where we see much better kind of tail latencies for this particular service. So by default, we try to keep low, or I guess utilization between the turbulent CPUs and the steady CPUs pretty much similar between two different groups of CPUs. But I wonder if it might make sense at lower utilization to try to keep more tasks off the CPUs with a lot of RQs in them, because then it would, because you can't predict when these interrupts are coming in, and they might affect your overall system progress differently if it's more interrupted. And the other thing we want to look at is how do we handle task stealing between these, what we call turbulent DSQs versus the steady DSQs, and what criteria can we use to decide some of these migrations? Do we look at, maybe what we can do is look at a historical graph of, okay, for these tasks that have this latency criticality, we can look at how long it's waited for this domain versus the other domain. And you can try to make a guess to decide when to migrate or whether to wait in the original CCX.
So how do you define that this CPU is turbulent? So this IOQ thingy or some other kernel threads, how do you track that in runtime?
So we look at just the IRQ time, and it's similar. Yeah, so this currently this threshold is a bit arbitrary. Right now, it's about if you're 15% of your time is spent in IRQ, we consider these to be more turbulent CPUs.
And then you set explicit interrupt affinities to create your turbulent CPUs.
Right. There's some RX steering that the service is using to try to keep cache lines local between the workers that they're talking to and the interrupts that are coming in. So there's some weird service level kind of thing that they're doing here to try to optimize. Other questions?
So this works if the fraction of turbulent CPUs is relatively small compared to the overall number of CPUs. Basically, what's the ratio between like turbulent and experiment?
So in this case, I want to say probably a third of the CPUs are turbulent. Yeah, so if all your CPUs are turbulent, you're kind of, there's not much you can do here. Your interrupts can come in. There's not much you can do about it.
Do you see some patterns for those CPUs, or kind of trusted? What's the pattern for those turbulent CPUs look like over time or days or?
So yeah, so the traffic will change depending on the time of day. It also depends on. But what we see is not a consistent stream, right? There are bursts that are happening from 1 second to the next. So these are not very,
They don't look like constant.
They're not really that consistent. They do fluctuate.
But as Peter pointed out, the network card is penned, so these IRQs are in certain cores.
Yeah, but it will depend on the day and night versus like how many users it's
the volume. Yeah.
I'm not sure, like with EVDF, I think the direction we're trying to go into is like what Vincent, I think, had earlier in the morning. So like we're trying to reduce the latency aware, which is basically based on slice to do task based and with the push load balance as well. So I think if the task have context switch, we can easily migrate it to different CPUs that can carry on running. Will not this fix your problem?
So you'd have to set the slice to 1 over your frequency to get duration, and then you get a big part of what LAVD does.
Yeah, so
you can get the same behavior upstream. I think what's missing is basically that at wake up, we just basically do task placement based on load, but that should be fixable.
Yeah, so I think LAVD also gives a bit of a preemption protection for tasks that wake a lot of other tasks, if I remember. Because if you get wakers to run, you get more parallelism or something like that. I forgot, but yeah, it has a number of heuristics. But the big one is basically having your slice as 1 over the frequency.
Yeah, I think yeah, that's my point. I think it should be doable with APDF. I don't see
they could probably do this and statically because they know their workload.
Yeah, it would be interesting to try Vincent's patches to use slice time as to improve like the scheduling latencies.
Yeah, and that also solves your inversion problem because your readers had a lower frequency because they were batching stuff, but you can still have it a smaller slice because you know your workload.
You're saying the smaller slice time for the reader?
Yeah, so you were saying that you had an inversion because your wake up rate of the reader was lower because it was batching some stuff, and therefore it was deemed less critical.
Right.
Even though it isn't.
Right.
And if you do manual slice settings, this goes away because you're not dependent on the heuristic of 1 over or the wake frequency.
I see. So you were suggesting is purposely reduce the slice of the reader such that you get.
For all your tasks, you can explicitly set the slice instead of relying on the heuristic.
We've gone a little bit in that direction with user space hinting. but had gone more towards hinting latency criticality directly rather than hinting.
Yeah, so I think with how V time is calculated, it's a combination of the slice time and also its latency criticality. So at least for us, I guess it depends on how important this wake or wake key kind of heuristic is in determining its critical chain. And what we found is, yeah, it works in some cases, and in some cases it.
So with SkidBench, actually using the SkidQS, the utility that I was working on, I found that actually even with the default behavior without a lot of changes, if I set the message to be user interactive, but the worker to be user initiated, which means the worker has longer time slice, that the message can frame them, I was getting better results.
Yeah,
So it's just basically what Peter was saying.
Yeah, so at some point, Chris gave me a SkidBench scenario that was particularly interesting for them. And I found that if you measure the work cycle and fit the slice to the work cycle and then use SkidBench, the whole thing reverts to FIFO and it does exactly what it wants to do.
Right. I'll hand it off to Ryan to talk about his new testing methodology.
All right, yeah, so part one, we went through a couple case studies of production apps. Now, as many of you know, debugging in production is always somewhat more difficult, especially if your only signal for your scheduled development loop is a sort of difficult, noisy, slow production experiment, unless your name is Brendan Gregg, perhaps. So what the rest of this talk is about is some general purpose testing tools that we've been developing to try to take a little bit more of our inner dev loop for schedulers further away from production. And of course, the dream is always something like this, that some nasty behavior is observed in production, but that you're able to somewhat quickly bottle it up as some simple reproducer that's portable, that you can run on dev machines, or that you can collaborate with your open source colleagues that don't have access to your production services. And a lot of the thesis of the remainder of this talk is that in this new agent-driven world, things like the simplification of a production scenario to a reproducer can be semi-automated through a combination of human and agent labor. And once you have your simple reproducer, hopefully the inner loop of your scheduler development, bug fixing, tuning your heuristics, et cetera, can happen in that tighter loop with a much more tractable development environment. And then, of course, when you come up with something that seems to work, you have to go back through the outer loop and validate it in production again. This is all kind of standard. But in our particular case, we're arguing for a somewhat complicated pipeline of simplifications, again, semi-automated and using agents, where we go from WPROF traces and some additional internal scheduler statistics that we capture in production. For example, I'm going to use this caching service as an example. And then what we do is we first try to we give ourselves the kind of freedom of expression of creating an arbitrary cartoon program in Rust, let's say, that attempts to reproduce the core scheduler behaviors that we saw in production. In this case, the IRQ case study that we just talked about, we want to see the same behavior of the LAVD latency criticality estimates and the same behavior of running on versus off the turbulent CPUs. And once we've confirmed that behavior, then there are various ways we can simplify. I'm actually a compiler person by training, so I'm used to, for example, taking a bug that crashes your compiler and trying to make a much, much shorter program that still crashes the compiler. Some compiler authors are very quick at doing that manually. In this case, what does it mean to simplify your reproducer? Well, for one thing, if you capture it on a machine with hundreds of cores, it's nice to simplify it down so it runs in a VM with a simpler topology. Maybe it runs on 16 cores with 2 domains instead of 300 cores. Once you have this bottled up version, runs in a VM, you can simplify it further. If you don't need the full expressiveness of that arbitrary program in C or Rust, maybe you can express your reproducer just as an RTAP spec. And I'm sure people here are familiar with RTAP, but I'll talk a little bit more about it on the next slide. At that point, you have a very kind of simplified domain-specific language almost for describing a workload. Once you run an RTAP, you can continue to run it in a virtual machine that's running on a real Linux kernel, or you can do this new option that I'm going to be talking about today, which is use something we just developed in the last few months called SCX Sim. And the idea here is that the language that SCX Sim speaks is the same grammar of workloads that RTAP runs, but it runs your scheduler completely in simulation with no live kernel and with completely emulated K-funcs. So it's bitwise deterministic. It allows you to connect traditional debuggers like LLDB, and we'll talk about how this works. If you're able to simplify all the way to that point, you have a very, very tractable environment for exploring the state space of your scheduler and using traditional testing tools on your scheduler. And then you can validate fixes there before you go way around the outer loop again. Okay, so I'm going to get to talking about the simulator for the remainder of this talk. That's going to be the bulk of what we talk about. But first, just a quick comment about RTApp. So over yesterday and today, I've heard multiple people refer to running benchmark workloads like SchedBench, Hackbench, et cetera. A lot of these are focused on a particular benchmark, like emulating a web server or something like that. They typically have some parameters, even the more specific workload focused ones like SchedBench, of course, has parameters. There are some highly configurable workload generators, like StressNG has many different instruction streams that it can generate, executing different kinds of ALU operations or what have you. RTApp is less focused on creating realistic instruction mixes, and is more just about what graph of threads that you have, how many of them there are, and how they communicate through mutexes and so on. It's pretty limited, doesn't emulate all the different ways that threads can communicate and wake each other, but it's good enough for some purposes. We have a version of it, we extended a little bit, ported it to Rust, added new features for things like IRQ stress generation.
Why could you not just work with the upstream RTF? Why you have to build a new one?
Oh, that's a good question. It's so small, it was easier to port to add a feature to it than to contribute. But yeah, it would be nice to. I actually think RTApp kind of sucks. Like I think as a DSL for describing different workloads you would have, it has strange limitations. Like it's not even valid JSON. It has unordered. It's order sensitive in keys. So it takes something that's supposed to be a map and tries to interpret it as a list. It probably would have been better as an S expression, which is ordered. I don't know. But anyway, the point is you can have some DSL for describing little graphs of tasks. And I heard somebody last night at dinner has a sort of RTApp replacement. It's not open source yet. So I could switch to that at some point. But the bottom line is there's some language of constructing a graph of sort of virtual user space tasks that burn some cycles and wake each other up and stuff like that. And in my case, we import these into the simulator. And so the way the simulator, so we should be able to take a single RTApp spec and then either basically reify it as real instructions. Like that's what RTApp is. It's an interpreter that takes in a JSON spec and transforms it into an instruction stream that appears on the CPU. So we can do that and run it inside a VM, for example, or we can interpret it abstractly in the simulator. And I'll talk about the architecture of this in a second. But the basic way that it works is it doesn't run any user space instructions. It just interprets the spec by saying, okay, this thing says it's going to spin for this many nanoseconds. So logical time jumps forward by that many nanoseconds. The simulator state updates and you proceed. And the cool thing about this is that what we do is that we run all of our schedulers in user space. So of course, our schedulers normally run with SEX, they normally run as BPF code. There are reasonable tools for debugging BPF, but not quite the same as debugging user space code. So when we run our schedulers in user space, we just take the C or the Rust code that implements the scheduler and we compile it with the regular compiler and have some extra wrappers that we link it to. And then once we do that, we can connect regular debuggers like LLDB. You can step through in VS Code. You can even do some time travel debugging with RR, Pernosco, that kind of thing. So you can get basically full godlike visibility into the state of your scheduler. You can pause the simulation. It's not sensitive to real time, et cetera. You can also do controlled concurrency stress testing, which is kind of my specialty that I'll talk about in a little bit, if especially because it might be something that people have less background with. Okay, and then at the end of the day, these both will produce Perfetto traces. And a lot of the development loop for the simulator is to just make these things match, right? And that is the kind of problem that I believe if we make it tractable and have sort of external validation, that agents can get better and better at improving the simulator as long as they always have that source of truth to look at what the actual kernel did, look at the Perfetto trace, and try to draw these things closer together. Okay, so how is the simulator architected? This is our normal picture to...
It's a trait. It's kind of like Kernel Shark, but it has a lot more features.
Yeah, it's a GUI crap.
It's a web browser.
Yeah.
Sorry, which one's kind of like Kernel Shark?
Perfetto is kind of like, it's like an extended version, like it's has other things.
Yeah,
I mean, it's much more complex than...
People keep saying that word and I'm like, what?
Yeah, we tend to use, well, it's from Google, I guess, originally for debugging Chrome. It's somewhat high performance way to load giant traces of events. That's pretty generic.
Does that work?
Sorry, which one? Awk?
Yeah.
Yeah. No, yeah, I mean, I guess the main thing is that you have a tracer like wprof or systang that can do high volume traces.
Kernel. A syskernel trace. Does that work?
Good question. I'm pretty new to kernel space, I have to confess, since last fall. So I'm still learning a lot of these tools.
Yeah,
I think it's trace stuff.
And
I mean, the trace information is extracted from the kernel interface, just that they add on top. Actually, Academy, to use that thing, you have to cannot download the internet on the box you're doing the experiment with, and then export it to Perfect. But essentially, it's using it.
Sounds like a pain.
Yeah, it's not like
that gives you some.
But you have to touch a
TUIs.
mouse, right?
Sorry?
You have to touch a mouse, right?
No, I don't use that mouse.
You can just use the command line and give a SQL request and query, and then you use that.
Well, to run it, you have Stutter.
Well, I'm sure you can.
I mostly just have agents use the protobuf representation of it on disk. Yeah. But anyway, the rough architecture of the simulator is, yeah, I mean, I'd be happy to talk about some of these trade-offs offline, and there might be other places where we could use some different trace format or something like that. Happy to swap stuff out or add compatibility. But, you know, if we take our basic cartoon picture of what we're normally doing with scheduling with SCADX, we've got the Linux kernel talking to user space through syscalls and context switches, of course. And then on the other side, it's invoking the BPF, the compiled BPF code for the SCX scheduler like LAVD. And it's making up calls into the scheduler via this vector of struct offs that is the interface to the scheduler that other people have talked about in kind of SCADX overview. And then, of course, the scheduler in turn can call back into the kernel via BPF helpers and kfuncs. And so if we want to switch this over to the simulator, how does it look? Well, now, as I mentioned, we compile the scheduler as just regular user space code. And once we do that, we link it to some extra C stubs that, first of all, just give us visibility into the internal state of the scheduler. So those are unfortunately per scheduler specific. This in general should work with any scheduler, but in practice, we make sure it's tested with all the different schedulers that exist in the SCADX repo. And so for LAVD, for example, there's some extra C stubs that give visibility for the simulator into the state of LAVD, like what are its latency criticality scores for different tasks, that kind of thing. And then on the other side, I mentioned how we run the RT-app spec symbolically, where we don't actually run any instructions. We just kind of directly interpret the graph. So that's what it looks like. Of course, the SCX sim is just a regular user space Rust program. So this whole thing doesn't require ring 0, all runs in user space.
So where does the topology come from?
Sorry, the topology information? Yeah, those are all kind of runtime parameters to the simulator. So there's this SCX sim binary. When you invoke it, you can have whatever kind of topology you like, however many CCXs and SMT disabled or not, and so on. And you run for some number of simulated nanoseconds. Yep. And by the way, you typically get a pretty big speed up over real time. So 3 to 10x, because you're not doing the actual work in the kernel and you're running all of the real cycles of the scheduler, but everything else is kind of mocked out. It does run sequentially, but you can run it in parallel. So instead of having a 300 core experiment take over your whole machine, like it does when you're testing on bare metal, you can run a bunch of parallel experiments, like one simulator per core, and explore different concurrency paths. This slide lost its animation.
Ryan, the output of the simulator is what? The traces, essentially.
Yeah.
The BPF trace that you feed into Perfetto, and then you see.
Yeah, it's a few different outputs. It reports its own kind of statistics. You can also turn on, Rust log equals debug and see all this stuff as it goes.
It's not just the trace; it's also other metrics. If I want,
it keeps track of some of its own metrics. So it'll spit out a CSV that reports scheduler latency statistics and things like that. So you can kind of either do trace analysis, or you can just directly spit out some of the statistics you might care about. I like the trace analysis because it kind of keeps us honest. We generate it from the live kernel and we generate it from simulation, and then all of our downstream analysis, it just looks at the traces and it kind of doesn't care whether it's simulated or real.
And I don't want to spoil, probably you're mentioning this, but how close is the Perfetto trace generated in the simulator versus Perfetto trace generated in a...
Yeah, I'll talk about that a little bit. It's far from a cycle accurate simulation, right? But we try to make it just kind of statistically accurate. So was the idle time and jitter, I've inserted a little bit of a statistical model of different properties of like wake up latency and IPI. And there's places we could go for a lot more realism, but I've attempted to kind of statistically model some of the costs. One of the places where I want to do a better job of that is with the K-funcs. Right now, here, I'll talk about this on this slide. Here, just imagine these appear one at a time. The animations got squashed by PDF export. But I wanted to say a few words about controlled concurrency testing. So this is something that's a kind of niche area. Examples include RR chaos mode. Has anybody used RR chaos mode or RR at all? Oh, okay. It was originally Mozilla RR, the record and replay debugger, but of course it's only for user space programs, so it makes sense. It wouldn't make as much inroads into kernel. There's also things like Microsoft's Coyote and various other projects from Microsoft, or my own Hermit project that we open sourced from Meta. When you're doing controlled concurrency testing, you're often explicitly exploring different interleaves into threads. So rather than just running on a multi-core and waiting for a race to occur, you're inserting chaos and delays in order to get more interleavings that would be improbable just to occur by nature, but that when you take control over the schedule, you're able to force more interleavings. And there's actually a lot of research literature on different forms of concurrency bugs, what their quote bug depth is, like how many ordering edges you need to expose them, and what the probabilistic guarantee of discovering those bugs with different controlled concurrency approaches are.
One of the Google guys is doing that in the kernel. They're using breakpoints to insert delays and stuff like that.
Cool, yeah. Yeah, that's similar to some of what Microsoft did in their kernel as well. Yeah, that's nice to see. I guess that's maybe the lightest weight version. As long as you can get some breakpoints and some hooks in, you can insert delays. That often gives you the ability to explore some new interleavings, but it doesn't give you determinism. So my favorite systems are ones where you combine this kind of randomized exploration with the ability to reproducibly not just run it once and get the crash, but to send it to somebody else and the same seed, the same input generates the same crash. That's where determinism comes in. So first, just briefly, like one of the basic assumptions here is that a lot of these systems actually execute sequentially, even though they're modeling concurrency. So what does that look like? In our particular case of SCX programs, they basically consist exclusively of a series of struct-op invocations across different CPUs. So we're modeling a system with 2 CPUs here. We're going to have struct-op 1, struct-op 2 on CPU 1, and then some other struct-op on CPU 2. The simplest simulator in the world might just execute each struct-op to completion. So that would not be doing a very good job of modeling concurrency, right? Because it would kind of artificially assume that CPU 1 struct-op finishes before CPU 2's begins. And in reality, of course, scheduling is highly concurrent. And even if you're doing your scheduling in BPF, it's running concurrently on a whole bunch of cores. So what we do is we run things sequentially, but we sort of use scissors and snip up the execution of these struct ops to break at arbitrary instructions or arbitrary branches. And once we've identified some preemption points, we can mix and match and achieve concurrency by interleaving as in the bottom picture here, where essentially the scheduler has its own event loop. It's running the simulated core with minimum logical time, and logical time is advancing on each core as struct-op code executes. There's always a question of how you do time in these simulated environments. For struct-op execution, time is a function of the retired branch conditionals times some coefficient. So that gives you a sense of like roughly how much work has the scheduler done. Unfortunately, on modern Intel and ARM architectures, x86 and ARM architectures, I should say, retired branch conditionals is the only deterministic measure of progress we can use because other things are affected by speculation and you can't reliably report the number of instructions. That's kind of a standard metric that's used by other systems like RR. So logical time advances as a function of the kind of simulated kernel behavior, the actual struct-op code that executes, and the K-funcs that you call. The K-func cost model could get more sophisticated. Right now, it's just kind of a lookup table that says each K-func costs this amount. We have a bunch of profiling data from K-funcs in the wild, and it'd be nice to put in a kind of statistical model that was extracted from that profiling data for more realistic timing in the future. But that's the basic idea of how we model a concurrent system by sequentially interleaving chunks of execution between different struct ops, and therefore being able to simulate racing operations and discover scheduler crashes that are a function of races. Now, for each one of these time slices of a given struct op that we execute, it receives control from the scheduler, and then it can give up control in 3 different ways. We already mentioned how the virtual time is a function of the retired branches, and the 3 ways we can yield are basically a randomized preemption point that the scheduler has decided to insert. And by the way, I love this sort of instrumentation implementation details of how you achieve that kind of preemption. We use this library called E9 patch, and I could talk about that offline for instrumenting our program, as well as a couple other alternative backends. Or you can give control back to the simulated scheduler, the underlying simulator engine, by making a kfunc call, at which point you switch over to the emulated kfunc, which, by the way, the actual instructions used to execute the kfunc are just an implementation detail of the simulator. You don't want to be charged for those. Instead, you want to have an abstract cost model for that part. Or, of course, the struct op can finish. So, of course, we're using pseudo random number generation to drive all these randomized decisions. So it's all repeatable. Same seed gives the same simulation, including the sort of preemption and jitter. The other kind of probabilistic aspects of it are all reproducibly deterministic. We already mentioned the pluggable cost model. Okay, so what are some of the benefits of this? We've already touched on some of them. Once it's bitwise deterministic. One of the things I love is BPF is kind of naturally restricting IO, which makes it a lot easier to make deterministic. The same is true of other systems like WASM. WASM doesn't have a lot of arbitrary IO capability, so there's relatively few surface areas that you have to lock down if you want it to be deterministic. In this case, we have to make sure that when you do grab the timer or grab a random number explicitly via BPF helpers, of course, we have to determinize those. We have to turn off ASLR. But other than that, this basically sequential code that becomes deterministic without a lot of extra heavyweight sandboxing. Runs faster than real time, can be run in parallel, as I mentioned, and the debugger integration. All right, now let's wrap up by coming back around to the caching service that David told you about in the first half of this presentation. So this, I think, is indicative of our general modus operandi for modeling. We identify the certain set of threads, in this case, these three threads, the worker, the reader, and the writer, that are kind of the foreground issue that we're interested in. We model everything else as just like, the other threads, the background threads. So for those, we're not trying to make a very detailed model. We're just trying to say, okay, how many active threads per core are there? In this case, about 3.8. And 70 threads per core total, but most of them are idle. And what percentage of CPU utilization do they contribute? So we model that cloud of background stuff in a roughly statistically accurate way. And we try to model all these foreground threads in a pretty accurate way. So the time slices should be representative, the wake-up frequency should be representative, and so on. So I call these our calibration parameters, where when we're trying to close the gap between production and the reproducer, and especially when agents are helping with this, we're trying to make these calibration parameters match as closely as possible. And those are kind of the independent variables. And then the dependent variables are things like the results of our experiment. What was the end-to-end latency observed? What was the sched latency observed? How well did we avoid the IRQ course? That kind of thing. I'm not going to spend a lot of time going through results here, but just to show one representative. This is an old version of the slide. It must have been cached from, is Google Drive open?
Yes, let me check.
Here, I'll just open it right here on Google Drive. I see, yes, it's 2018. OSPM 2026. There's a day 2 thing, right? Slides. Day 2. Cache invalidation. Yeah, I'm just gonna. I wanted to present just one very simple subset of results. We have lots of different modes that we run in here because, as I mentioned, we did have that pure Rust reproducer, and then we put it in a VM, and then we compare the RTAP version in a VM versus in simulator. But this is just simplifying and cutting it down to just our production versions. And looking just at this one parameter, I mentioned multiple independent variables, multiple dependent variables, but just looking at this one dependent variable of IRQ exposure, how much time did the worker tasks spend on the IRQ turbulent cores? So the pre-IRQ LAVD was pretty bad here. We're spending 21% of its time on the IRQ turbulent cores. And then post the IRQ improvements, it went down to 6.6. And those metrics are computed from the traces that were gathered in production, whereas the simulator saw pretty similar numbers that are consistent, where the pre-patch version of LAVD was spending more time, higher IRQ exposure, and we got a very similar fix. The things never match perfectly. First of all, we have the problem that when we have noisy services that are changing traffic patterns, when we take our traces from production, we get different behaviors when we get different traces. So it's kind of a question of what exactly you're trying to fit to with your reproducer. That's one source of complexity. Also, the system's not perfect. You can see we still have a gap in CPU utilization here. The simulated CPU utilization doesn't perfectly match this trace that it was calibrated with. So that's room for future improvement. But hopefully you get the basic idea about bringing these close together and then having all of our debugging tools available in the simulator. One final comment on the simulator. This actually came originally out of Joseph Basic. I don't know if anybody knows him, but he was at Meta until last year. And last summer, he started trying to introduce some mocked K-funcs so he could write unit tests for some of our schedulers, because our scheduler code is normally not unit tested. So we essentially only have end-to-end tests, which kind of sucks. Like even our self-tests, you have to produce a whole scheduler and run it to test anything. So this was kind of taking that idea to its logical extreme. Instead of mocking a few K-funcs and writing a unit test, why not mock all of the K-funcs? And then you can do unit tests, or you can run sort of full simulations. And one of the fun things about that is you can just tell the agents to try to increase code coverage. And right now they're at about 77% code coverage on LAVD, but they've gotten pretty good at identifying branches in the LAVD code and then trying to create test scenarios that exercise those branches to get the code coverage up. So that's it for me. Any questions would be welcome.
Regarding this utilization gap, do you add some penalty when you preempt the task in the simulator and then you basically run a bit longer the former task because of the context on the CPU that you destroyed? Maybe that's the reason. Then you would see this in the production as a real utilization, which is growing. The task that you cut in half or something, then that would be longer to recover and then get the IPC from the CPU.
Yeah, right now there are models for this stuff. So if I remember correctly, the some of the extra overhead we have around context switch is modeled as a log normal process, which might be kind of unfair. It has an unfairly long tail, maybe. It's randomized, it's not just a constant, but there's also just a ton of parameters. So right now, they've got defaults, but you can like pass in a bunch of parameters to the command line that control all these different simulated overheads. And that part probably needs a lot more work to try to make it realistic. Right now, it's just been tuned so that, when earlier versions of the simulator, things would be far too clean. It had far too little simulated overhead, and you get extremely low scheduling latencies. Like the scheduler would just execute really quickly. And we basically have, over time, put in more sort of simulated overhead and simulated delays. So, but right now, some of it's too simple. Like if you migrate to another core, you take a little user space hit that's just kind of a guess at a locality penalty. But the one thing that's totally missing here is any modeling of memory. So we don't know what the locality penalty would be or how much cache you use. Maybe that's something we could improve our model a little bit. Even if we don't have individual cache line information, we could try to characterize from our production apps what some of the memory behavior is and which are more migration vulnerable threads.
Yeah, I was going to say that for this production utilization, you might record in the trace the IPC from your counters and back install on your counters when you migrate task. Then you could see that the task is actually waiting for the new CPU to catch up.
Yeah, no, I think that'd be really interesting. Any kind of aggregate statistics around that you can get from PMU counters seems really valuable to sort of abstractly characterize the workload without having to get into the detail of actually recording the instruction stream and try to reproduce that instruction stream. So yeah, that's basically the sweet spot that we're going for, is like how much more qualitative detail can we get while it's still an aggregate picture rather than some kind of full instruction stream trace. It'd be hard to reproduce. Thank you.
I was interested in the agentic loop that you showed as an introduction. Is that like very ad hoc for each type of workload, or do you like have like a set of prompts you're using for making to like and then convert it to eventually RTF? Is that something that is available open somewhere? Because I think certainly would be interesting.
Yeah.
To play with that.
Yeah, that's a really good point. So I think our team in general has been trying to like share our skill files more, and I think our company has a reasonable track record of trying to crowdsource these things more. But during the initial phases of vibe codification, it felt like everybody had their own setup and there wasn't enough sharing going on. This is a good example of that. So right now they're not actually in the open source repo yet, but we should indeed sort of move some of the prompts we're using into there.
I think it would be interesting for the community because I mean, apart from maybe you're not interested in using the simulator, but the idea of coming from like workload collecting traces and then have something that simplifies that so that you can actually run the same simplified version and maybe have it like shared within the community would be really interesting to see.
Yeah, I'd love to work with anybody who's interested in that. That was indeed my original fascination, was like, as we all know, like these coding agents are fabulous at some things and super dumb in other ways. So is this process of monkeying with a candidate reproducer to get it closer and closer, is that something it could do? And my gut feeling was like, we can put enough guardrails, which is proved out somewhat so far, is that we can put enough guardrails around the process that you don't have to trust the agent too much. It can continue to hallucinate crazy shit constantly. But if you have enough kind of external guardrails on it, you can, at the end of the day, that like Perfetto trace that comes out is a non-falsifiable form of evidence to some, for the most part, and you can get it to get closer over time. And all of that should work fine with open source tools as well on our stack.
And the other thing is maybe we want to stop the proliferation or RTF, like different versions. It would be nice to have. I'm not against a Rust version. I think ARM also has had one, but I think it might be nice to have like one version that maybe it's superior to the current, let's say, RTF version. Again, collaboration would be nice.
Yeah, for sure. For sure. That's definitely a challenge in this software is free era, is actually collaborating.
So, as a complete AI noob, I was wondering why all these MD files are in a separate repository and disconnected from the code. Should not they just be code comments that the AI reads, or how does that work?
Yeah.
It seems silly to have comments for humans and comments for the machine be different or separate and duplicate and stuff like that.
Yeah, 100% agree. So, and of course, with Claude in particular, it's always hard to fight back against its desire to constantly vomit more MD files into your repository that quickly grow out of date.
I've never seen a Claude, so I have no idea what it does.
Yeah, for example, I've been using recently the review prompts from Chris Mason, and that thing, I'm not sure what his intent is, but that thing can live somewhere in the kernel. I mean, they are essentially text files. We have a documentation written text files, and I guess if it's useful, we can have something like that, or even like
everything. Yeah.
Yeah, I mean, Claude, to take one example, does encourage norms around this. Like every repository should have a claude.md, just like you have a contributors file and a README, and that tells Claude how to navigate your repo. And you can also have a .claude file that is within the repo that has all these skill files and whatnot that are associated with the repo. So yeah, when people are doing a good job of like organizing their AI configuration, I firmly believe it should be version controlled alongside the code. Same goes for tasks, actually. So there's now 10 million different agent-oriented local task managers. It started with beads, but now there's a bunch of other versions as well, because these agentic loops need some task management outside of their little memory that's built into Claude. So having some CLI access to a task manager, which in my preference it lives in the repo as well, is another part of the picture. So the skill files, the instructions, the prompts, and then the task management can all just get version controlled. Oh.
So you said that the loop was part human and part AI. So what's the human part?
Yeah, that's a good question. I think the human is mainly there to yell at the AI when it's doing dumb things repeatedly. Which I wonder if there's any kind of vibe coding burnout after a year or so, after correcting the same things 1,000 times. But you always dream that you're going to get the right prompts and the right skills that will prevent these superficially plausible wrong hypotheses sprouting so frequently.